Hey everyone, welcome back. This is part 2 of finding inverse functions. In the last video, we were solving for exponential inverse functions, and in this video, we're going to solve for logarithmic. But just real quick, I'd like to recap what we started off the last video with. As we are finding inverses, we needed to remember what we know about them. For example, we know with inverses, properties of inverses are that the x and y variables swap. Remember, x is all possible domain values are x values, and all possible range values are y's. So if these two variables swap, then the domain and range for a function and its inverse swaps. And because of that, the graphs are reflected across the line y equals x. Lastly, we know that inverses undo each other and can be treated like operations. For example, addition undoes subtraction, multiplication undoes division, and logs undo exponentials. And just as we can say the forward direction is true for all of these statements, the reverse direction is also true. So in today's video, we're going to solve for inverse functions of logarithmic ones. So we're going to use the fact that exponentials undo logarithmic equations in this video in searching for f inverse of x. So again, we are still solving for inverse equations. This video is specifically focusing on logarithmic functions. And our goal is going to be, given an equation or a function, given a function f of x, our goal is to find the inverse equation and we're going to call it f inverse of x. Remember, this notation is not a negative exponent, although it looks like it means f inverse of x. And just like last time, I have the step-by-step process of how we would find logarithmic inverse equations. Remember when we were dealing with inverses in semester 1, we had a pretty clear-cut process, and the same process follows through for what we're doing right now. We're going to first rewrite the function that's given to us, f of x, as y. Then we're going to switch our variables x and y because we know that that's a property of inverse functions. Then we're going to use inverse operations to isolate, in this case, the log function, since we're going to start with a log. Then to undo the log, we're going to need to exponentiate both sides. And lastly, solve for y, apply any other inverse operations if necessary. Finally, wrap it up with a bow. Make sure we're practicing using f inverse notation. Make sure we're using our function notation to help us get more familiar with what the task is at hand and comfortable with what we're writing. So let's start off with a pretty basic example. Here I'm going to say, what if our function f of x given to us is log base 2 of 3x plus 10, okay? Let's say this is our log function that's given to us, and our goal is to find the inverse equation. So step 1 says to rewrite f of x as y. So f of x, I'm going to say y equals log base 2 of 3x plus 10. Step 2 says to switch variables x and y. So y becomes x, keep everything else the same, but x becomes y. Notice that I literally only changed the variable. Everything else remained the same. Log base 2 remained the same, 3 remained the same, plus 10 remain the same. It's very, very, very important that we are only switching the variables x and y. Everything else stays the same. Step 3 says to use inverse operations to isolate the log. Now, if you watched the previous video, you'll know that my strategy is to find the exponential and circle it. In this instance, let's find the log and circle it so that we can get it isolated. Here, the log's a little bit complicated, but that's okay. It kind of helps us identify that all we need to do is get rid of this plus 10. The inverse operation of addition is going to be subtraction, right? So in step 3, I'm going to subtract 10 from both sides. So on the left, I'm going to have x minus 10 equals log base 2 of 3 to the y. Cool. Step 4, though, now that I have a log alone, I'm going to have to exponentiate both sides. Just like we were taking the log of both sides, we're going to have to exponentiate both sides. And just like when we took the log of both sides, we're going to have to choose the base that the log has. We're going to have to choose the base that the exponential should have, right? So the base of my logarithm is 2. That's going to be the exponential base that I exponentiate both sides. So 2 raised to the x minus 10 power is equal to 2 raised to the log base 2 of 3y. This is how I signify me exponentiating both sides. The base of my exponential function is 2 because the base of my log function is 2. Since exponential functions and logarithmic functions are inverses, 2 raised to the log base 2 cancels out, leaving 3y is equal to 2 to the x minus 10. Now I'm on the process of solving for y. I need to get y alone. And in order to undo 3 times y, I'm going to have to use some inverse operations. And the opposite of multiplication is division. Whatever I do to one side, I must do to the other. So now I have y is equal to 2 to the x minus 10 over 3. And lastly, we want to write this with our function notation. So f inverse of x is 2 to the x minus 10 over 3. Take a moment to notice the log function we've started with and the exponential function we ended with. What do you notice about the equations? Are there any connections you can make between what the log function looks like and what the exponential function looks like? Let's do another example. Okay, let's do another example. I'm going to just do it right over here on the right-hand side. And let's start with f of x is equal to log base 5 of 3x plus 4. Okay, our goal is to find the inverse equation of f of x. So step 1 says to rewrite f of x as y. So y equals log base 5 of 3x plus 4. Step 2 says to switch our variables. X equals log base 5 of 3y plus 4. Step 3 says to use inverse operations to isolate. Notice that this is already done. Yay! We love it. And the way I could verify that is I'd find the log and make sure the base and whatever the input is completely alone on one side. There's nothing being added, subtracted, multiplied, or divided to it, so it is isolated. Next step is kind of the hardest step for us, exponentiating both sides, mostly just because we haven't gotten enough practice yet. So step 4 is to exponentiate both sides. What is the base of this logarithm? the base is 5. So the base of my exponential function, or the base of my exponentiation, is going to be 5. So 5 to the x equals 5 to the log base 5 of 3y plus 4. Since logs and exponentials with the same base are inverses, I end up with 5 to the x equals it's kind of my Rapunzel moment again. My exponent gets released 3 to the y plus 4. And now my goal, step 5, is to solve for y. Again, I'm going to use inverse operations to get y alone. So let me find y, and it needs to be alone. Okay, so I need to get rid of this 3, and I need to get rid of this plus 4. I am going to start by subtracting 4 on both sides. I end up with 5 to the x minus 4 equals 3y. And to get y alone, I'm going to have to divide both sides by 3. Whatever I do to one side, I have to do to the other. And I'm left with 5 to the x minus 4 over 3 is equal to y. Yay, I've got y alone. Lastly, I need to use my inverse notation. Therefore, f inverse of x is 5 to the x minus 4 over 3. Again, what do you notice about this logarithm that we started with and the exponential function we ended with? Take a second to observe the original function and the log function, the original function and the exponential function. I apologize that I keep putting my box straight through my exponentials. What connections can you make? Let's do one final example of a logarithmic function. Okay? Let's do one final example of finding a logarithmic function. I'll move my paper down. And let's see. So what if I gave you f of x is equal to the natural log of 4x minus 8 minus 7. And I ask you to find the inverse. This is still a logarithmic function. Notice that this is still a logarithmic function because a log with base e is the natural log. So something you're going to want to take note of is log base e is equal to the natural log. That base e is going to come in handy later. So let's start. Even though this looks kind of complicated, let's just continue following our step-by-step procedures to find this inverse function. Step number 1 says write f of x as y. Remember, from function notation, f of x is representing the output value, and output values are represented by the variable y. So y is equal to the natural log of 4x minus 8 minus 7. Step 2 says to swap our variables, because remember, domain and range switch, x and y switch, it's reflected across the line y equals x. Everything remained the same, just the letters of x and y swapped. Problem 3 says use inverse operations to isolate the log. Remember, log now has base e, it's the natural log. So find the natural log, find its input, and put a box or circle around it. Anything that is not in the circle or box of trust needs to be moved with inverse operations. In this instance, I'm going to have to undo subtracting 7. Well, the only way I know how to undo subtraction is by adding. So let's do it. Whatever we do to one side, we must absolutely do to the other. So far, I have x plus 7 equals the natural log of 4y minus 8. Notice that now my natural log is alone. It's completely isolated. That's all I needed to do. Now for step 4, exponentiate both sides. What is the base of the natural log? Yeah, the base of the natural log is e. So if the base of a natural log is e, what will be the base that I use to exponentiate both sides? E. I'm definitely going to use e to exponentiate both sides. So since the base of the logarithm, you can even kind of put in a little e there if it helps you remember, is e. So I'm going to exponentiate both sides with base e. E to the x plus 7 is equal to e to the natural log of 4y minus 8. Now, since log base e and exponential base e are inverses, I end up with e to the x plus 7 equals 4y minus 8. And again, step 5 says to solve for y. Do everything to isolate y. I like this little trick. Grab it. I'm going to have to undo this subtracting 8 and undo this multiplying by 4. Now, order of operations is pretty important. I'm kind of doing reverse PEMDAS to get y alone. So I'm going to add 8 to both sides. Careful when I do this as far as notation. Okay, I still have e. The entire exponent is x plus 7. But I just added 8 to this, so it is a big plus 8. Equals 4 times y. Make sure you don't do this plus 8 up here. You have to be careful of what your exponent is. Lastly, to get y alone, I need to undo multiplication. So I end up with y equals e to the x plus 7 as the exponent plus 8 divided by 4. Oops, kind of ran out of space there. And y is alone. Yippee! Don't forget to use our function notation. F inverse of x is equal to e to the x plus 7 plus 8 over 4. If you wanted to reduce this 8 and 4, that is fine. However, know that 4 is the denominator of e to the x plus 7 as well. So usually we're just going to keep it like this. But if you're really crazy about splitting it up and you really want to, it would actually look like F inverse of x is equal to e to the x plus 7 over 4 plus 8 over 4, and 8 over 4, of course, reduces to 2. So you would have F inverse of x is e to the x plus 7 over 4 plus 2. So you decide which looks prettier. I prefer to just have it like this with one single common denominator, and I think you will enjoy having that too.